This class is an introduction to systems of equations. So a system of equations is when you've got multiple equations with multiple unknowns, so multiple variables like an x and a y or an x and a y and a z. So when you're starting this topic, you'll see 2 by 2 systems, so 2 equations with 2 unknowns like an x and a y. Maybe further down the line you'll see 3 by 3 systems with an x and a y and a z, but they're already quite a bit more complicated and beyond the scope of what we're going to do here. So the first thing you need to know is that you need to have as many equations as you've got unknowns. If you had, for example, just that top equation, we can find infinitely many solutions to that. It's not that we can't find any solutions, we can find too many. So without that second equation, which provides another constraint on the x and the y value, you could find a whole bunch of combinations, in fact infinitely many combinations to satisfy that equaling 8. So we need that second constraint, or if we had an x and a y and a z, we would need a third constraint to stop the x and the y value just being anything that you want it to be. So you'll always see 2 equations if you've got 2 unknowns. If you don't have that, then something's not right about the question. So that's the first thing to know. The second thing to know is that we also refer to these as simultaneous equations, especially for the 2 by 2 case. They're quite often called simultaneous equations because we're solving them simultaneously. We're solving for an x and a y value, which is true for that equation, but also true for the other equation. Generally, when you move beyond a 2 by 2 to like a 3 by 3, so an equation, 3 equations with an x and a y and a z, we tend to no longer call that simultaneous equations, we call that a system of equations. But they're all simultaneous equations and they're all systems of equations. So refer to it in either way that you wish, and you'll see it written both ways in textbooks, but for the 3 by 3 and above case, it will probably be called a system of equations. So in this class, we're not going to get into the technical details of how we solve these. It's a fairly simple algebraic process, and we'll start looking at that in the next class. We just want to think a little about the overview of this topic. So we know that we need multiple equations, as many as we've got unknowns. And let's think a little bit about the solutions. Well, the solutions could be any type of number, positive, negative, fractions, decimals. Usually they tend to be whole number solutions, especially when you're starting off this topic, but they don't have to be. Just like normal equations, it can be any of those other number types. But if you think about the structure of these are actually in the format of a straight line, y equals mx plus c, but just jumbled up. So let me just quickly label these, equations 1 and 2. If I take those equations and rearrange them, so if I start with equation 1, I can rearrange that to, well, let's just work through the algebra. So if I move the 5x to the other side, I'll get minus 5x like that. And then if I divide through by 2, I'll get minus 5 over 2x plus 4. So that's just a rearrangement of equation 1, so we'll call that equation 1 again. And then for the second guy, if we take the 2x to the other side, we would get minus 2x plus 5, and then divide through by minus 1, which just changes all the signs. We get a positive 2x and a minus 5. So that's a rearrangement then of equation 2. So now these are in the format y equals mx plus c, like a straight line. So these are actually the equations of straight lines. So what does that tell us? Well, if you think about it, if you're trying to find a solution to that equation, it's just an x and a y number. A number for x and a number for y. But if that's a straight line, then that x-y combination has to be a point on the line. If you're finding the same x-y combination to satisfy the other equation, then that's the same point on the other line. In other words, the only point that satisfies both that equation and that equation, i.e. the only point that lies on both lines, is the point where they intersect. So when you're actually solving these systems and you get an x value and you get a y value, what you're actually finding is where these two lines cross over, where they meet the point of intersection. So if I just quickly sketch these up, and we'll see if we can get a rough estimate for what that solution might be like. And I mean, like I said earlier, this is an algebraic process to solve. I mean, you would never be asked to use a graph to solve this accurately. You might be asked to make a graph to sketch a rough guide to the solution, an estimate basically for the solution. But you would always solve these algebraically. But let's just have a look at this. So this first line here, it's got a y-intercept of 4. So let's say that's up about there somewhere. It's got a minus 5 over 2, so minus 2.5 gradients. That's sloping down to the right and fairly steep. So it's going to be something like that. So that's line 1. Let's do the same for line 2. Y-intercept of minus 5. So that's going to be down here somewhere. Gradient of positive 2. So that's going up kind of steep to the right, maybe like that, just roughly. So we can see that those lines do intersect. One had a negative gradient, one had a positive, so they have to intersect at some point, and the point appears to be somewhere around here. So it's not very far along to the right, and it's not very far down. So putting a very rough scale on that, if that was 4 up, then we might say that that's like 2 or 3 along the way. So this point's maybe, let's just say it's roughly 3 along the way. Down the way, it seems to be very close to the x-axis, so let's say minus 1. So we're saying that roughly, I mean, that's just a very quick sketch, but the point appears to be around 3 minus 1. So what that tells us, if that's where they intersect, then the solution set for this set of 2 equations is somewhere around x equals minus 3 and y equals 1. So we could just check that. If we take, for example, the second equation, 2 times minus 3 is minus 6, minus 1 is minus 2 times minus 3 is negative 6, minus 1 is negative 5. So that's not right. I didn't expect it to be right, but we're just trying to get a rough guesstimate for the solution. If we take the other one, 5 times minus 3 is minus 15. Oh, I'm sorry. Look, I've put a minus 3 in there. It should be the other way around. I did think those numbers were a little off, so yeah. So trying that again and being more careful. So 2 times 3 is 6. Minus 1 would be a plus 1. 6 plus 1 is 7. So our guesstimate comes out to be 7. So that's a lot better. That makes more sense this time. So that's a pretty decent estimate. Let's check it again with the other one. So 5 times 3 is 15. 15 minus 2 times 1. 15 minus 2 is 13. So it's not quite right. I didn't expect it to be right, but it's in the ballpark, which is what we're basically looking for, just a guesstimate. We don't really ever use that method to find solutions. We just use it to maybe guesstimate them and to have this graphical interpretation of the equations. So all that I really want you to take from that, other than the fact that I make mistakes, is that when you're solving simultaneous equations, what you're actually finding is this point of intersection of the 2 lines. If you moved up to a 3 by 3 system where you've got an x and a y and a z, an x, y, z equation is not the equation of a line, it's the equation of a plane. So a plane is like a sheet of paper or something like that, and it carries on forever and forever. When you've got 3 of those, you've basically got intersecting planes. So it would be like where the bits of paper cross over. And then there's a third one going in some other direction, which I'm not going to attempt to draw. But they're much more complicated. So the point is that every type has got a graphical interpretation. For the ones that we're looking at, a 2 by 2 system, 2 by 2 simultaneous equations, it's both straight lines and you're just finding the point where they meet. So that's just an overview of what systems of equations are. I've tried to there talk a little bit beyond just the 2 by 2 case, which is definitely where you'll start to think a bit about how this might work if you ever move up to, for example, a 3 by 3. But just remember that you need as many equations as you've got unknowns, and that for the 2 by 2 case, which is where you're starting, these are actually the equations of straight lines, and that all you're doing is really finding the point of intersection. So with that in place, let's maybe think about the technique. And the technique is not too difficult, and we'll start to look at how you solve a 2 by 2 system in the next class. So when you're ready, check that one out.